Well, good afternoon. I'm sorry I'm late. It's 11:47, so 17 minutes late getting started. But I had so many students hanging around after my last class, and some of them had long, complicated questions and issues going on. So I just was able to get to the office to swap out books and just get a little something to stave off the hunger and thirst for a bit. And then I came back up here as soon as I can. So sorry I'm late getting started, but it's just been crazy all day long. If someone gets here, I'll talk about how crazy it is. But anyway, picking up where we left off before, we're in Chapter 4, Vector Spaces, 4.1, just barely got started last time. And here we're doing at the top of page 148, example 3, operations with vectors in the plane. So here's a vector V, and again, I think I've mentioned to you before, this author and the other two books that I teach by the same author always puts vectors in angle brackets. In this text, he puts them in parentheses. So if I put an angle bracket, understand that's a vector. But I'll try to write it the way he does here. Here's vector V. Let me get my pen set up. Okay. Vector V is negative 2, 5. This is a two-dimensional vector. And vector U is 3, 4. Okay? It says find each of the following vectors. The A one here says what is 1/2 of V? Well, you can just write it exactly like this. 1/2 of vector V. Well, vector V is the vector negative 2, 5. Now, again, usually when you see two numbers with a in parentheses with a comma between them, you think a point in the xy plane. That's not what we're dealing with here. We're dealing with a vector because it says it's a vector. Okay, so understand that's a vector. And what you do is take 1/2 of 1, so it would be negative 1. 1/2 of negative 2 is negative 1, and 1/2 of 5 is 5/2. That's it. That's all there is to it. Negative 1, 5/2. The B says U minus V. U minus V. Well, do it exactly what it says. U is the vector 3, 4, and that's a vector, minus a vector V, which is a negative 2, 5. Okay? Now I'm going to do it underneath it, so hopefully it'll be even clearer. This will be a vector. The first component is 3 minus a minus 2, so that's 3 minus a negative 2, comma. Well, we have a student. Amazing. Okay. Tyrell is here. Last time I had one student for just the last few minutes of the class, but I'm glad you're here. Let me go over just a few things first. Let me turn on the projector and turn off the lights. All right, for today's class, this is the last day of class. Monday and Wednesday classes, we still have class on Monday. Okay? But today's the last day of class for Tuesday, Thursday classes, which is us. So we're continuing here. Before you leave today, let me return all your papers to you that you've turned in. It doesn't count the research paper because they periodically ask for samples of student writing, so I have to hang on to that. But for your test is what I'm talking about, which also means, I can't remember, you did turn in your research paper for this class, or did you?
It was differential equation. Yeah, I think it was this class.
Okay, I can't remember. Let me see if I got you down.
It was for one class, I know.
I don't think I have one for you for this one, unless you turned it in recently.
No, I still need to send me the paper for this.
I don't think I have one for this one.
Yeah, that's fine. I can put it up on my flash drive.
Okay. All right, because I knew I had gotten one from you, but I didn't remember which class. But I don't have a grade for you, so I don't think it's this one, unless it was very recently. because I'm behind in grading right now because things have been crazy the last few days. Okay, so today's the last day you can turn that in and not lose points. Okay, and technically today should be the last day you turn in any of your other tests, but I will accept them, but get them to me as soon as you can. Okay, and I already gave you the test on determinants, right?
You know I'm not finished, don't you?
What's that?
You know I'm not finished, don't you?
Okay, well, did you put not finished at the top?
I'm sorry. I just have to be to work at 12. I'm going to be late, Dr. Fowler, but it's okay.
I'm sorry?
I got to be to work at 12. And it's already, what, 11:51 or something?
I don't know what time it is. I don't have my... Oh, yeah, here's my watch.
It's 11.
52.
Okay, I'll be a few minutes late. That's okay.
Okay.
I just did the ones that I know, like,
Okay.
makes sense to me.
Okay.
And you said you be on the Birmingham campus?
Tomorrow,
You going to be in
8
this?
to 12.
You going to be in that office where I seen you at the last time?
Probably. It's room 122.
Yes, sir.
Dr. Pruitt's office.
Okay, and I'm going to come down there and I'll look for you.
Okay, between 8 and 12.
Yes, sir. I'll be
Okay.
there.
Okay.
Thank you.
Uh-huh. So, yeah, I gave you the Chapter 3 test, which is determinants.
Yes.
I don't know, we're going to get covered in Chapter 4 what we can today. I don't know if we'll get far enough along that really it's going to be worth having a test, so that may be your final. Okay? Certainly, the final just means the last test. Okay? So, sorry we didn't get any further, but it's been kind of crazy.
I see you tomorrow, Dr. Fowler.
Okay.
Thank you.
See you tomorrow. Okay. It has been like this all day long. I have had students just all over the place. On top of that, my first class, the class outgrew this classroom, had 37 people, and this only holds 30. So we had to move down the hall to 205. That's why that sign's been on the door all term, Math 112, 205. Went there, well, when I got here this morning, all but one classroom on where my office is on that hall down there was locked up. Well, it was like that last Monday too. They had just forgotten to unlock the doors. Well, this time they said, no, we're not unlocking any classes until the instructor gets there. I said, well, there's students out in the hall. Well, we don't care. Okay. What happened was I came up and checked mine. And 205, I don't have a key for that. I have a key for this one and 259 because I use those. But I didn't have I used to have a key for 205, but I gave it to somebody. I don't remember who now, and they haven't returned it to me. So I don't have that anymore. So I had to go down and tell them, well, I needed one at 205 open because I had a student waiting to get in. And so she came up to do it. She said, oh, that's the room that the projector was stolen from. So that meant I couldn't teach the class this morning there because I needed a projector. So I had to move the big class in here, but not everybody showed up today, so they all fit. So, but it's been crazy all morning long. Students have been going all over the place, supposedly looking for me and going to the wrong room or whatever. And then people coming in to take tests, turning in quizzes that were due months ago. I mean, it's just been absolutely nuts all day. So it's going to take me probably hours to sort through all the things and get them in the right order because they've just been piling things in from all sorts of classes. I hope I haven't lost anything, I'll put it that way. Okay, so anyway, it's been a crazy day, and there still may be more interruptions. So anyway, so it may wind up that last test I gave you, which was what? Did I give it to you Tuesday or, no, last week? Thursday. Okay, well, that may be your final exam. So okay, now, are you graduating this term?
I am.
You are. That means I have to have everything you're going to turn in to me in, but all classes, by Thursday.
By Thursday.
Yeah, of next week.
Next week.
Yeah. Sooner is better than later, but sooner, but by Thursday. I can't accept anything any later because your grades have to be in by noon on Friday. Have to be. Otherwise, you may not be graduating. Okay. So get everything into me by Thursday.
I'm going to try to have everything in. Probably my paper in by today.
Excellent.
Yeah, hopefully by today. But the test probably no later than Monday.
Okay, excellent. Way to go. Okay. All right. So that's taking care of a couple things there. So let me give you basically what my schedule is going to be, so you'll know where to find me and what I'll be doing. Today is a regular class day, so I'm in class until 5:45 today, okay? Because after this class, I have 30 minutes for lunch, and then I have my mini-term physical science class, which is 2.5 hours of class and 2 hours of lab. So that's 4.5 hours, 1:15 to 5:45. Now, we may finish a little early today, so I might be in my office a little before 5:45, but it's not going to be by much, if at all. Okay, tomorrow, Birmingham West Campus, Dr. Pruitt's office, B122 Academic Building, from 8 to 12. I'm usually there before 8. I'm almost always there after 12. I can't be too late tomorrow because I've got to drive to Georgia tomorrow, so I don't want to be too late leaving. Okay, so that's tomorrow. Monday is a class day, okay? They got it in the final exam schedule wrong. Everything was right otherwise, but on the final exam schedule they put it wrong. It is a class day. So I'm going to be in my office from...
I think it might be my son.
I'm in my office from 8 to 10, and I'm in classes pretty much from 10 till 3:45. I do have 45 minutes for lunch and 20 minutes in between the next two classes, but that's it. And then I'm in my office again from basically 4 to 6. Okay, so that's Monday. Tuesday, final exams start for full-time classes, full-term classes. So I have a final Tuesday morning down in 205 from 8 to 10. Finals start on the hour, not on the half hour. So if you have an 8:30 class, those finals are 8 o'clock, not 8:30. So just word to the wise. So that class, the final on Tuesday is 8 to 10, but it's 8 to 9:50, but I'll be in that room from 8 to 10 at least. Excuse me. Okay? Then after 10 o'clock, I don't have anything else scheduled, so I'll be, Tuesday. Don't have anything scheduled from 10 until 1:15. It's because I'm teaching a mini-term class that we still have classes on Tuesday, not finals, okay? So I'll be in class from 1:15. I doubt if I'll be in class till 1:45, but that's when 5:45, because there's not going to be a lab that last day of class, or if there is a lab, we'll finish earlier. But allow 1:15 to 5:45, but if I'm through before 5:45, I'll be in my office until 6. So that's Tuesday. Wednesday, I don't have any finals scheduled, so I'll be in the office from 8 until 4. Because at 4 o'clock, I leave to go to the Birmingham East Campus, and that's where the students from my physics class will be turning in their work. So I'll be there from 4:30 to 6:30 on Wednesday. Thursday, I have, again, nothing scheduled from 8 till 1, okay? So I'll be in the office from 8 to 1. But at 1, I'm giving the final for my physical science class. So we'll be up here from 1 till however long it takes. It's not going to be a very long final, so it won't be till 5:45. So whenever the last student's finished, then I'll go back to my office, and I'll be there until 6 o'clock. Then Friday of next week, and you have to have everything into me by that Thursday. Friday of next week, we have, I'll be in the office on the Birmingham campus, 8 to 12, basically. Okay? The Monday of the following week is the last day of finals. So but you already have to have everything into me by then. So I'll be in my office here from 8 to 6. Okay? Now, Tuesday is supposed to be just a duty day for us to get everything graded and all the grades in. Because Wednesday is when everybody else's grades have to be in by noon on Wednesday. So I'll be here basically 8 to 6 again. I won't be needing to go to the Birmingham East Campus again on Wednesday. I think we still have a duty day on Thursday. So I'll probably be here all day Thursday, 8 to 6 as well. Friday, I'll be on the Birmingham campus again, 8 to 12, But graduation is at 1. So I'll be over there from 1 till graduation's over. So that will wait.
How long does the graduation go?
Okay, wait. Let me back up. Oh, usually about 2 hours, maybe more, maybe less. Let me back off from that. I may be wrong on that because I think we have a nephew graduating, getting his MBA at LSU. I believe that Thursday. So I may have to take a personal day that day because we're driving the grandparents. They're going to come down to Birmingham from Huntsville, and we're taking them to Baton Rouge because they're in their 80s and they can make the drive okay, I think, but driving around Baton Rouge on the graduation day is not an easy thing to do. It's a madhouse there, and I don't think Mr. Brazil wants to do that. So we're doing the transportation. So I know I'm going to have to go. So I probably will miss your graduation. Sorry about that. I know that's heartbreaking. Okay, now that's pretty much the schedule. I think the following week we have off, and then summer term begins after that. Not immediately. We have to be back one day and then some, or a couple days for registration. All right, what we're doing on page 148, chapter 4, vector spaces, 4.1, vectors in Rn. Right now we're just in R2, which is 2 space. And for these 2 vectors, vector 1, now in your other classes, now you're not in linear algebra, are you?
No.
Have you already been in that?
I am.
Yeah. We can't get rid of her, can we?
They're not in your car?
I have them, I just.
What is it? What is it? What you looking
Car keys.
Car keys?
Yep.
Haven't seen them. And they're not in that chair or anywhere around there.
I didn't see the stuff right now. I don't see a few.
That's where they were.
I didn't touch the stuff.
That's your bag, right?
Yes. I don't know what it would be.
No, she, I think, been panicking because of him and the term time all day, but okay. So I may have to go clear my head. That sneezing attack is loosening too much up now. Right. So I'll be right back. Let me put this on pause. Yuck. Sorry about this. Okay. Now, did you take linear algebra already?
I'm taking it now.
Oh, you're taking it now.
That's
Okay.
all.
Right. Yeah. Okay. But you're already finished with Cal.
Yeah, I'm done with Cal.
Wait, this is linear algebra. You're doing Cal. You're already finished Cal 3.
Yeah, I finished Cal 3.
You're in differential equations in this. Okay. But if you remember from, were you in my pre-cal class too?
Yes.
Okay.
Pre-Cal 3.
Yeah.
Yeah.
Okay. Remember, Ron Larson was the author of that book.
Yeah.
The calculus book, he was the author of that. And in every other book, he puts vectors in angle brackets. And if you see parentheses, you understand that to be a point, with these coordinates of a point as opposed to components of a vector in angle brackets. Well, in this book, Linear Algebra, he puts vectors in parentheses. Same author, and he does it this way. So those are vectors, okay? You have to read from the context whether they're vectors or points. These are vectors. There's vector v, -2, 5, and vector u is 3, 4. So what we're doing on the b part here, I already did the a part, we're doing vector u minus vector v. In component notation, which is the way to go, that's the way to do with vectors, that's 3, 4, that's vector u, minus vector v, which is negative 2, 5. How do you subtract vectors? You subtract them component by component. So your first component of your resultant vector, the difference, is going to be 3 minus a minus 2, that's what I've written here, then comma for the second component, 4 minus 5. Okay? 4 minus 5. And for some reason, my pen's not writing. Okay. So what is 3 minus a minus 2? 5, comma, negative 1. There's your difference between those two vectors. Okay? The C part says, that makes us here. Now, just sorry about the rehash here. Are you graduating this term? No. Okay, you are. Okay, and I can't remember if I said this before. Have y'all done the student course evaluations? Yeah, I did. Yes, good, fantastic. Okay. Now, we're in 4.1. We barely got started in 4.1. I don't know if we're going to cover enough material for me to give you a test because today's the last day of class. So your determinants test, which no one's turned in yet, that probably going to be your final exam, your last test. Test 3.
When did you guys over?
Last week?
Yeah, last week. Oh, I didn't.
You didn't get it? No. Okay. Well, let me give that to you then. And while I'm doing this, let me go on and return these papers to you. There's your test.
I still need to print it.
Huh?
I got mine on my email. I need to print it off for you. I was going to ask you, could I use your printer after this?
Oh, you mean the research papers?
Yes.
Okay, I mean the test papers. Let me return these to you. And that looks like that will be the last test, which by definition then is the final test. Okay. All right, we're in 4.1 now. The C part of this is example 3, top of page 148. Says what is 1/2 v plus u. 1/2 v plus u. Well, we already did what 1/2 v was. We can get back from number A. That's going to be negative 1 5/2 plus u. Well, u is 3, and it's 3 comma 4, right? That's u.
Yes.
Okay? But because the second component in 1/2 v is in halves, I want to write 4 as 8/2. Is that okay? Okay, so let's just do that. 8/2. That's still 4, right? So I haven't changed anything. And now again, you add components. You want me to write them out, or are you okay adding them in your head?
1 negative 1 plus 3.
Yep.
So it's
2, comma.
3 half.
This is 5/2 plus 8/2. 13 halves. Okay, now that's one way to write it, and I think that's probably how they do too. I'm sorry, my head is still draining like crazy. Oh, sorry. Okay. So that was example 3. Making great progress today, aren't we? All right, so let's go through. Any questions on this? All right. Let's go through fairly quickly this theorem 4.1, which is properties of vector addition and scalar multiplication in the plane. Okay? Now, here we have U, V, and W are vectors in the plane, meaning two-dimensional vectors, x's and y's. Okay, these are vectors in the plane, and C and D are scalars. Okay, these are vectors. Okay, and C and D are scalars. Any old numbers, any real number in the world. The 10 properties here. Okay, first, U plus V is a vector in the plane. If U is a vector in the plane and V is a vector in the plane, then the sum vector is going to be in the same plane. Well, that makes perfect sense because you add component by component. And if you have only two components for U and only two components for V, when you add them, you only get two components in the sum, and that's going to be in the plane. Now, this has a special name. This is called the closure principle of vector addition. Okay? They just say closure under addition, but I'm going to put closure for vector addition. That means when you add two vectors, you get a vector in the same space. Now, we're just saying plane now, later we'll say space. It could be 3 space like the room. It could be 17 space, which is just a mathematical concept, but it's still that. And believe it or not, Muhammad is here. See, I told you he would be in. You said he wouldn't, but yeah, okay. Okay. And by the way, I need papers in today. Research papers, tests, all those kinds of things. Okay? Yeah. That might work for a gal, but it won't work for me. Okay. Okay, good. All right. There's the first property, that vector addition is closed in whatever space you're dealing in. This is in the plane. Here's a second. U plus V is exactly the same as V plus U. And that is the commutative I'm going to abbreviate it, property of vector addition. Commutative property of vector addition. Okay, it doesn't matter the order in which you add vectors. Add U plus V, same as V plus U, you're going to get the same result. Just like with real numbers. Okay, 3. U plus V plus W is the same as U plus V plus W. Okay, it looks like we might be getting some rain soon. Okay, sure. It's not a great pencil, but you can certainly borrow it. Or that one too, I didn't even notice that one. Okay, now this is the associative property of vector addition. Okay, property of vector addition. Okay, now what that means, it doesn't matter if you're adding 2 or 3 or more vectors together, it doesn't matter how you group them together when you do the adding. Whatever works best will do. Okay, the first one says it doesn't matter the order, the second one says that, the third one says it doesn't matter how you group them. You can add 2 that are easy to add and then add that to the third. It doesn't really matter. Okay? Now, the fourth one says that U plus the vector U plus, now that's a bold 0, meaning it's the 0 vector. Okay? Anytime you add the 0 vector to a vector in the same space, this is in the plane now, 2 space, because the 0 vector is just 0, 0. Okay, so you add u, which is u1, u2, to 0, 0, you get u1 plus 0 is u1, and u2 plus 0 is u2. That's just u. Say again?
It's going to give out the same vector.
Okay.
So if you have a vector 0 to a vector, also will give you the same vector.
You get the same vector, exactly. And that is the additive identity property. I'm sorry, I can't write. Additive identity property. That there is a 0 vector. There has to be. It sort of drives me nuts because the definition of a vector is a directed line segment which includes that it has a magnitude and has a direction. Except for the 0 vector. 0 vector has 0 magnitude and no direction whatsoever. Because how can nothing have a direction? It doesn't matter which way it's pointing, it's still nothing. Okay? But you have to have it to be a space. And we haven't even talked about that yet. That's what this chapter is going to be talking about. Okay, number 5. If you have a vector u and add to it the opposite of u, then you get the 0 vector. And that's a vector, not the 0 number. And that is the additive inverse property. Okay? Additive inverse property. Number 6. Cu is one of these scalars, any old scalar, multiplied by a vector in the space is going to be, is a vector in the plane. Okay? That is the closure under scalar multiplication. Okay? Closure under scalar multiplication. That's number 6. Okay? Number 7. The first 5 we're dealing with sort of adding vectors. The last 5 are dealing with multiplying scalars by vectors. Now this is one of the sort of distributive properties. If you distribute a scalar over the sum of 2 vectors, u plus v, that's the same as c times u plus c times v. Okay? You just distribute the outside across both of the things on the inside. Okay? So that's a distributive property. I'm going to call it the distributive property of scalar multiplication over vector addition. Okay, number 8, another multiplier. This is doing sort of a different version of that. Here you have 2 scalars, c plus d, multiplied by a vector, is it u or v? U, okay? U. Okay. This time, you distribute the vector over the 2 scalar addition. So that's c u plus d u. Okay? So that's distributive property of scalar addition over scalar multiplication. Or scalar multiplication over scalar addition, either way you want to say it. Number 9. Now, this one is notable for what they're not saying more than what they are saying. If you have a scalar c, I don't need that opening parentheses. I thought they were going to phrase it the other way. Okay. C multiplied by du, that's the same as cd times u. They put the parentheses there. Okay. Now, that is one form, of, associative property. That's the associative property of scalar multiplication by a vector. Okay? So if you have two scalars and one vector, it doesn't matter what order you do. You can do the scalar times a vector. So this is a vector. Scalar times that vector will be a vector. Or you can pull these two together and multiply those two first, the two scalars first, and then multiply that result by the vector. You still have a vector. Okay? And they're the same values. And the last, number 10. 1, that's the number 1 times the vector u is always going to produce the vector u. Okay? That's the multiplicative identity property. Okay? Just like you had a additive identity property, which was the 0 vector, the scalar number 1 is a multiplication identity property. Okay? Any questions on that? They do a little proof here for the associative property of vector addition, and they do one for the distributive property of sum of two scalars over a single vector. So you can look at those if you'd like.
These are your basically all those the forms 1 to 10.
Say this again.
All those the steps 1 to 10 that we have to follow.
Are these what?
All those the steps 1 through 10 as well.
They're not really steps. These are just 10 properties of vector addition and multiplication. Okay. And they're all talking as if these are in the plane. Okay? The very next thing we're going to do is extend this to any dimension. 3 space, 7 space, 45 space. Okay. I can't interpret those for you, but they do them in the book. Okay. We live in 3 space.
Yes.
The plane is 2 space. But there's all sorts of abstract math that goes into higher level spaces. Yeah. But it's very abstract. It's not anything real that I can imagine. Anyway. So let's move next to vectors in Rn, which is precisely what we're talking about. Okay? The discussion of vectors in the plane can be extended to a discussion of vectors in n-space. Pick a natural number n. 2, 3, 7, 13, 45, whatever. You can talk about an n-space, a vector in that space. What that means, that vector will have either 2 components, 3 components, 7 components, 45 components, whatever. But every vector in that space will have the same number of components. Okay, now I can visualize x, y, and z. I can see pretty clearly x, y. Okay? But anything beyond 3 space, I have no way of referencing it except just doing the math, doing the numbers, dealing with them the way they are. And those 10 properties we just had, they work in n-space. That was for 2 space. Certainly works for 3 space, but it works for n-space. Okay? So in an n-space, what we have, rather than an ordered pair or an ordered triplet, which you would have in 3 space, we have an ordered n-tuple. It's sort of like they just made up a word, n-tuple. Because you say double, triple, and then you would say quadruple, quintuple, so they say n-tuple, okay. Any natural number you want to put there and put a tuple after it, okay. Ordered triple would be x1, x2, x3. Now, quite often for an ordered triplet, we would say XYZ, and that makes more sense to me, but you could put it numbered things, okay? Ordered quadruple, yep, would be x of 1, x of 2, x of 3, and x of 4. And then anything you're doing with that, you would have to also have vectors with 4 components, okay? Now again, these are vectors, even though those are parentheses. In this text, he uses those to represent vectors. So a general n-tuple, okay, an ordered n-tuple would be x of 1, x of 2, x of 3, comma, dot, 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 all the way up to and including x of n. That's an ordered n-tuple. Whatever n you want to put there, natural number, you can put it there. So the set of all n-tuples is called n-space. Okay? That's what n-space is, set of all n-tuples. Okay? Now, we denote that by r superscript n. That doesn't mean raised to that power, though there's a little bit of that concept in there, okay? It just means what we've been dealing with 2 space, that'd be r superscript 2. Space would be r superscript 3, okay? And then n space would be r superscript n, okay? So let's give just a few of these. R super 1 would be 1 space, and that would just be a set of all real numbers. Okay. R2, that would be 2 space, and that would be the set of all ordered pairs of real number. Okay, real numbers. Okay, now, I usually call that a plane. I usually call R1 the number line. That's all real numbers are represented by that one line. 0 somewhere in the center, and 1, 2, 3, 4, but every point in between from negative infinity to positive infinity. That's a set of all real numbers. That's a straight line. 2 space, set of all ordered pairs of real numbers, that's your plane. All positions on a plane, going infinitely in every direction. Okay? R3, and I usually call it R3 rather than R superscript 3. This is 3 space. This what? That's what we live in. You're absolutely right. And that's the set of all, and mathematically speaking, ordered triplets of real numbers. What's that? X, Y, Z. That's what I usually talk of it. They would typically say X of 1, X of 2, X of 3. X, Y, Z, same deal. Okay. Yeah. But when you get anything higher, then you have to come up with some other number. There's no number after Z in the alphabet, so you have to go before, and we usually say X, Y, Z, W, and then X, Y, Z, W, V. And then you have to back up even further. So, and soon if you get more than 26, you run out of letters. So what they do is just do X1, X2,
So they
X3.
can use Chinese characters.
What's that?
They can use Chinese characters.
Chinese characters? Is that what you said?
Yeah.
Okay.
I got more than 1,000 of them,
Yeah.
so you can keep using.
Help yourself, okay? Okay? Just don't turn them in on a paper I'm grading or expect a bad answer. Okay. A negative
That's going
outcome.
to be my math invention.
What's that?
That's going to be my math theory.
Oh, I see. Okay. I'll look forward to reading it. Okay? Now you can continue this on up until you get R super N. Okay? That is called N space. Okay? And that is defined as a set of all ordered N tuples of real numbers. Goodness gracious, pain in the neck. Okay, all N tuples of real numbers. Okay. Okay. And again, just like they did before and continue to do, if you only see a parentheses and then a series of variables, and I don't know whether to use the subscripts 1, 2, or 3, whatever. Let's just do X, Y, and Z. X, Y, and Z. Okay? That would be in 3 space. Okay? That, if you just see it, if you just see something like that, your first assumption would be that is a point in space. Okay? Unless there was something that indicated to you it was something other than a point in space, you assume it's a point in space. But if they tell you those are components, if that's a point, those are coordinates of the point. 1x, 2y, 7z. Okay? That would be a point somewhere right up there. Okay? But if they tell you that's a components of a vector, that would be coming from the origin pointing to that point. So a vector is going to be an arrow pointing that way to that point. The point itself is just those 3 coordinates. Those are coordinates of a point or components of a vector. Okay? Again, this book doesn't make a distinction in how they write those. Okay? Now, remember before we listed 10 properties of vectors in the plane. They're going to sort of shorten that a little bit and talk about the standard operations for any vector in Rn. That's what we're going to do now. It doesn't negate the other things, but it just sort of shortens it and sort of deals with it. So let's say we have 2 vectors, u, and this is going to be in N space. So this first vector is u1, u2, u3, ... up to u sub n. Okay. And vector v is going to be v1, v2, v3, ... up to v sub n. Okay. These are 2 vectors in R sub n. Why R sub n? They each have n components. If one of them had n and one had m, they're not in the same space, if m is not equal to n. But if they're got the same number of components, they're vectors in the same space. And we're going to call that Rn. Okay? C is a real number. We often call a scalar, meaning a number with no direction. Vectors have magnitude and direction, except for the 0 vector. Okay? Then the sum is defined as the vector u plus V is equal to just as we did before, U1 plus V1, comma, U2 plus V2, comma, U3 plus V3, my goodness gracious, my pen and my writing, between the pen and my writing, it's getting almost illegible. 3, okay, comma, dot, 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 comma, up to U sub n plus V sub n. So you've got to have the same number of components before you can add those. So if one was n and one was m and they weren't the same, you can't add those vectors. It's not defined. Only, and no matter how big the space is, how large the n is, as long as it's a finite number, you can talk about these two vectors in that space, and then the sum of those two vectors would be the sum of each of their components, but their components have to be the same size. Okay? So that's what we call scalar addition. Vector addition. Okay? The second part is scalar multiplication. Yuck. My pen really drug then. Okay. Scalar multiplication of U by C is then defined as CU, just like we would expect. Okay? And what would that be? Because U is n components, this would be CU1, comma CU2, yuck. Well, let me write it here. Comma CU3, comma dot, 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 comma goodness gracious, CUN. I've been having trouble with my cataract, and every now and then I just can hardly focus on anything. I already had my right eye fixed, but it's a long lens. Once they put an artificial one in there, it doesn't adjust anymore. So it's only for distance. So I can't read anything with my right eye. My left eye is my short eye, so my brain takes care of all this most of the time. But right now, I've got a blood spot in this cataract, and so every now and then, things just don't look right, and I have to really strain to get it to focus. I'm going to have this repaired in June, or it may be May, but once that happens, then I don't have any adjustment at all. I have to adjust it with my head to get in the right place.
Why would you do it? Why not leave it alone?
What's that?
Why not leave it alone?
Because it gets foggy, it gets clouded, and I can't make out things. And especially reading on computer, like right now, I can hardly make the computer focus. I have to get down here to make it focus because the cataract is messed up.
Glasses will help.
What's that?
How about glasses?
They will only correct so far, but the cataract is messing it up. Now, I could do glasses with this eye and bring it closer. That would work. But then I'd be fighting. This eye would be trying to do one thing and this the other one. And it does cause for some issues. But supposedly once I get the second one fixed, I'll be okay. And here's Daniel. But, haven't we got just like 1 or 2 minutes left? Okay. So let's get done what we can. Now, as with two space, the negative of a vector in Rn is defined as this. Minus u would be minus u1, minus u2, minus u3, comma, dot, 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 comma, minus u sub n. Okay? That would be the negative of a vector in space. Okay? So the difference of two vectors, here's the sum of two vectors. The difference of two vectors, u minus v, would be just like we've done before. That would be the vector u plus the opposite of vector v, which is exactly how we add sign numbers, or subtract sign numbers. You do the first one plus the opposite of the second. And that's exactly what we do here. And I'm not, well, yeah, I guess I will have to write it all out. They do. This would be the vector u1 minus v1, comma, u2 minus v2, comma, u3 minus v3, comma, dot, 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 all the way up to u sub n minus v sub n. Okay, that's how you subtract two vectors. Okay, and the zero vector in n space, I'm going to put sub n. Okay, I don't know if this is what the book is going to use, but that would be the vector that's 0 for the first component, 0 for the second component, 0 for the third component, all the way up to and including 0 for the nth component. You have to have n zeros there. Now this seems a little bizarre.
Wouldn't that just give you the same vector? Like a point?
Yeah, it's just a single vector with no magnitude and no direction. So basically it doesn't seem like a vector at all, but you have to have it. And by the way, it is a vector, so it has these components. But it doesn't go anywhere. Like you said, it's a single point. No direction, no magnitude. Not heading any direction and has absolutely no zero magnitude.
Okay, I have a question.
Yeah.
We over time. We passed time, but I have a question.
Okay. What's the question?
All right. This right here.
Is the question asking me to determine, like, to tell you what happened, or you want me to, because I'd find the determinant, and I noticed the determinant was the same. The only thing happened was in row 2 and row 3 was swapped. So do I have to explain that?
Okay. Determine which property of determinants the equation illustrates. Okay. And I think you just said it. When you exchange either two rows or two columns of a matrix, the determinant, it negates the determinant. That's the property.
So I need to write what happened down if that's the question.
Okay. Determinants of elementary operations. That right there.
So I need to write the
what property that illustrates.
Oh, okay. Because
Yeah.
I just found the determinant of it, and I drew it, and then what I did was, I found the determinant, and then observed and noticed that's what happened.
It's just saying what property does that illustrate.
Okay.
Yeah. And I think you said it, but write it down. Yeah. Okay. Now, if I'm not mistaken, we are now out of time, right?
Yes, we are.
Okay. So your third test is your final exam in this course. I need the others in today, the first and second test, and if I don't get your research paper today, then you start losing points if it's turned in tomorrow or any other later day. So please, now I returned some people's papers earlier, and I've only received one research paper. I can't return these to you because they periodically ask for samples of student writing, but I think the other two people who have turned anything in, they're not here. So I need the first two tests from two of you. And I'll take the third test anytime you've got it. Okay?
What's the last day for the third test?
What's that? What was the question?
Last day for the third test.
What's the last day for Thursday?
For the third test.
Oh, for the third test. Oh, okay. I explained that earlier. Okay? And here's what it is. Are you graduating this term? No. Okay? I have to have, if you're graduating this term, I have to have everything in by Thursday, 1 week from today. If you're, and that's, Terrell is graduating, so he has to have everything in by Thursday. If you're not graduating, the last possible day to have the third test in is next Monday, the following Monday, not this coming Monday, but the next one. Because that I have to have everybody else's grades in by noon on Wednesday. I have to have graduate grades in by noon on Friday. I have to have everybody else's grades in by noon on Wednesday. So I need everything in by Monday if you're not graduating. But I need the first two tests today because I've already returned them. So technically, you should be getting zeros if I don't have your first two tests by now. So I'd like to have them in. Okay, I've been telling you all this all term, right? Okay, so got it ready? I'll take them. Okay, I gave you yours right there.
Yes.
1 and 2. Okay, good.
No one got theirs back left yet, because...
What's that?
Just making sure it still counts.
I'm sorry, I can't understand what you're saying.
I was making sure that no one left before I'm turning this in, so you know this thing.
Okay. They're all still here. I don't understand it. Okay. So anyway, get me your stuff, preferably today. Okay? And we're out of time. Any final questions? And just as a future reference for you, because some of you came in after I announced this to the other folks, well,